Ya, Assalamualaikum warahmatullahi wabarakatuh dan selamat sejahtera semua bertemu kembali. Okay, we see chapter 7, internal flow. Okay, for example, fluid flow in a pipe. Okay, pipes with diameter D and then a pipe length L. So E is a surface roughness of a pipe, and then a fluid with density rho, okay, viscosity mu. Okay, flow through in a pipe. Okay, then V maximum velocity at the center line of pipe. So small cap u we call local velocity, and then one more velocity V bar. So this is for average velocity. Okay, we use Reynolds number Re to determine the classification of flow, whether laminar or turbulent. Okay, so Reynolds number, we know the Re is equal rho Vd over mu. This means dimensionless. Okay, rho Vd over mu or equal Vd over nu, where nu kinematic viscosity equal mu over rho, viscosity over density. And then if Reynolds number less than 2000, so the flow is laminar. Okay, and then the Reynolds number between 2000 to 4000, so we call transition, okay, from laminar to turbulent. And then for Reynolds number greater than 4000, so the flow is fully turbulent. And then in the piping system, they have two losses. Okay, okay, first major loss we call major loss. Okay, major loss due to viscous resistance or viscosity. This means friction factor F. So from Darcy-Weisbach equation, so head loss, okay, HL equal F L over D V squared over 2G. So F is dimensionless, friction factor due to viscous resistance, and then L, so pipe length, D is a diameter pipe, so V squared over 2G. V is mean velocity of fluid in the pipe, so G is a gravity 9.81. Okay, and then F for laminar. If laminar means Reynolds number less than 2000, so we use this formula. So F equals 64 over Reynolds number for laminar. For turbulent flow, when this means the Reynolds number greater than 2000. In practice, we use when less than 2000 laminar, and then greater than 2000 we consider as a turbulent. So when turbulent, so we find out F friction factor from Moody diagram, okay, or Moody chart. And the second losses we call minor loss, okay, due to piping fitting, okay, or components. Okay, for example, valve, elbow, T-joint, okay, pipe entrance, okay, pipe exit, and etc. So we use a K, symbol K, means minor loss coefficient. So HL, head loss in the piping system, equal K V squared over 2G. Okay, and then delta P, okay, delta P is a pressure drop, okay, from Bernoulli equation. Okay, for example, in this case, okay, 0.1 between 0.1 and 0.2. Okay, so P1 over rho G, this means pressure head V1 squared over 2G, okay, velocity head plus Z1 potential head. And then at point 2, so P2 over rho G, okay, plus V2 squared over 2G plus Z2 plus HL is head loss in the piping system. Okay, for case pipe is horizontal, so Z1 equals Z2, so cancel. Okay, so P1, okay, minus P2 over rho G equal V2 minus V1, V2 squared minus V1 squared over 2G plus HL, head loss. When the diameter D1 equal D2, okay, that means B1 equal B2, so cancel. So the rest is P1 minus P2 or delta P, okay, or pressure difference, okay, over rho G equal HL. Okay, in this case we call delta P is a pressure drop. So delta P over rho G equal HL. So HL from Darcy-Weisbach equation, so equal F L over D V squared over 2G. And then for piping system, okay, when involve pump, so efficiency of pump equal output power over P input power. Output power, okay, for pump equal rho GHPQ, okay, over W dot P. Okay. This is rho G, HP is a head pump, Q is a flow rate or discharge. Okay. Means energy transferred to fluid or liquid. And then W dot P is power required to drive the pump. Okay. Let's you see an example. Okay. We use a pump here, pump to deliver or lift, for example, this is water from tank A to tank B. Okay. And then diameter pipe, let's say diameter pipe 2.5 cm, and then pipes made of cast iron where E is the surface roughness, equal 0.26 millimeter, and then length of pipe 100 meters, and then the efficiency of pump equals 70%. Okay. And then K1, that's mean loss in the pipe entrance. So K1 equals 0.5, K2, K5, and K6 is a elbow or pipe bend. Okay, all K2, K5, and K6 equal 1.5, 1.5, 1.5, 1.5. And then K3 and K4, okay, K3, K4 equals 0.24, 0.24, 0.24. This is valve, gate valve or fully open. And then K7, okay, losses at pipe exits, okay, equal 1. Okay. And then elevation at pipe elevation mean from datum, okay, to free surface at tank A, so equal 10 meters. Okay, and then elevation at tank B equal 50 meters. Okay. Then if water at temperature 20 degrees C, so rho equal 998 kg per cubic meter. So mu density equal 1 times 10 exponent minus 3 kg per meter per second. And then Q, flow rate or discharge, okay, Q equals 0.005 cubic meter per second or 5 liter per second. Okay, the equation is okay, determine the power of pump, mean power required to drive the pump to deliver, okay, or to lift the water. Q equal 0.005 cubic meter per second. Okay, first we can calculate velocity in the pipe, okay, from discharge or flow rate. Okay, equation Q equal AV. So V, that's mean the velocity in the pipe, so Q over A. So Q 0.005 cubic meter per second over A area, diameter cross-sectional area of pipe, pi over 4 in diameter of pipe, okay, 0.025, okay, squared. Then we get a velocity in the pipe, okay, equal 10.2 meter per second. And then we find out the Reynolds number to determine the type of flow. So from Reynolds number, R equal rho Vd over mu, so rho 998, okay, V velocity 10.2, and then diameter 0.025 meter, mu 1 times 10 exponent 3, okay, minus 3. Then we get Reynolds number equal 2.54 times 10 exponent 5. That means greater than 2000. So the flow is turbulent. Okay. For turbulent, we can find out F friction factor in the piping system. Okay. Okay. We use this using Moody diagram or Moody chart. Okay. Okay. First, we determine the E per D or relative roughness. E. Okay. Because a pipe made of cast iron, so E is 0.26 millimeter. Okay. So 0.26 times 10 exponent minus 3. So over diameter of pipe 0.025. So we get a 0.0104. Okay. Okay, you see a Moody chart or Moody diagram. At left side, okay, friction factor, and then at a vertical line, okay, Reynolds number, okay, and then at the right side is E per D, relative roughness. Okay, first we see Reynolds number. Okay, Reynolds number equal 2.5 times 10 exponent 5. Okay, okay, when we see at the Moody diagram or Moody charts, it start here 1 times 10 power 5. Okay, and then 2, 3. So 2 got 2.5 here. So Reynolds number equal 2.5 times 10 power 5. Okay. Okay, this is a vertical line. Okay, and then E per D. Okay, the graph a curve there. Curve E per D. Okay, relative roughness 0.0104. About 0.01. Okay, this curve. Okay, then the intersection line between the E per D and the Reynolds number. Then we bring horizontal left side. Okay, we can read F friction factor. So F we get 0.038 between the 0.03 and the 0.04, and then we can substitute into the Bernoulli equation, and then from Bernoulli equation between point 1 and point 2 at free surface. Okay, point 1 P1 over rho G plus V1 squared over 2G plus Z1 plus HP, because pump give energy to the fluid. Okay, so HP at left side. Okay, and then at point 2 P2 over rho G plus V2 squared over 2G plus Z2 plus HL at losses in the piping system. Okay, P1, P2 cancel because P1 equal P2 equal PATM. Then B1 equal B2 also cancel because very small. Okay, going down, so B2 going up, and then so HP. Okay, we want to find out HP. So HP equal Z2 minus Z1. Okay, then plus HL. Okay, Z2 minus Z1 plus, so HL total head loss here. Okay, first from friction factor, so F L over D V squared over 2G plus because by fitting, so total K V squared over 2G, and then Z2 minus Z1 plus KV K constant, so V squared over 2G times F L per D plus total K. Okay, so Z2 elevation equal 50 meter. Okay, 50 meters minus okay, Z1 equal 10 meters. Okay, V1 10 okay, 0.2 okay, squared over 2G. G is gravity 9.81 time. So L, okay, this is F 0.038. Okay, and then L 100 meters, D okay, 0.025 meters plus okay, total K, that means K1 plus K2 plus K3 plus K4 plus K5 plus K6 plus K7. So all total is 6.48. Okay, and then you calculate, you can get HP. Okay, 880. Okay, 880.38 meters. Okay, this is HP or heat pump, and then we substitute to formula WP. Okay, from efficiency okay, of pump equal P out over P in. Okay, P out equal rho G HPQ. Okay, divided by efficiency of pump. Okay, rho 998, G is 9.81. So HP equal 880.38, and the Q flow rate given 0.005. Okay, so equal 5 times 10 exponent minus 3. Okay, divided by efficiency of pump. Okay, 70% has been 0.7. So we get W dot or power required to drive the pump. Okay, equal 61.57 kilowatts. This is power required okay, to drive the pump, okay, to lift or to deliver water with Q equal 0.005 cubic meter per second. Okay, thank you.